Hello friends, welcome back to our channel. So today we'll see one more concept in compiler design, that is issues in designing the code generator. So in our previous session already we have seen different phases of designing a compiler. So in that, lexical analyzer, syntax analysis, semantic analysis, and then the intermediate code generation. And now the next phase is a code generator, target code generator. So before generating the target code, so what are the design issues we need to focus? So that is our concept. So let's start the session. Issues in designing code generator. So the first issue is, so this is the next phase of intermediate code generators. So we are having some intermediate representation of the code. So first we will start from the source code, and now we are at the intermediate representation of source code. And our next the next output and the next generator is the code generator. See, the first design issue is input for the code generator. Input for code generator. So already we know what is the input for code generator. So the first one is a 3 address code. 3 address code. So actually we can call it as a intermediate representation. So we have studied about the intermediate representation. The code can be represented in different ways. That is a postfix notation, 3 address code, syntax tree, as well as a directed acyclic graph. So there are a lot of representations. Among that, we are saying this 3 address code will be the optimized one to generate the code, okay, target code. So the first input is a 3 address code, and also the symbol table. So in our first sessions of compiler design, we have seen the complete phases of compiler design. In that, the two things are common for each and every phase, that is a symbol table and error handling. Okay, so these two are the inputs for the code generator, and if this 3 address code is not correctly written, automatically that will be reflected on the code generator. So the 3 address code representation is most important. And the second one is a target machine instructions. Target machine instructions. So here we are generating the code for a target machine. So the different machines will be having a different architectural styles. Okay, so whether it is a RISC instructions or CISC instructions, so reduced instruction set or complex instruction set. So we need to focus on this one. So whether the target machine is having the following the reduced instruction or the complex instruction. So based upon this, the code should be generated. And the third one is a memory management. Memory management. So we know that there will be different kinds of memories. So in that we'll be using a normal memory, similarly heap memory, and the registers. Okay, so our source code will be using a different identifiers, functions, etc, etc. So which should be stored in which memory. Okay, so that should be very careful, because the accessing should also be very fast. Okay, so when compared to this one, we know that registers are very fast to access. So when we have to use the registers and what kind of variables we can store into the registers, so that we need to focus before generating the code. Next, register allocation and assignment. Register allocation. So we know that when compared to the memory, registers will be very less in size but very fast accessing. Okay, so less in size, fast in access. So we need to, and also the registers are limited. The registers will be in a limited number. So we need to take care the which variables should be assigned to the registers and which variables should be allocated in the memory. So in order to get the fast access. So usage of registers, usage of registers, because these are less in size, fast in access, and also limited number of registers will be available. And the next one, instruction selection. Instruction selection. So as we discussed it just now, the target machine will be having a different architectures. So which kind of instructions should be selected? For example, so for let us take, if you want to implement this one, a is equal to b plus c. Okay, so you can implement this one by using simple add instruction, add a comma b comma c. Okay, and the same thing, see, this kind of instruction, if you are using this kind of instruction, we can use add a comma b. So here we are using 3 addresses instructions, and here we are using 2 addresses instructions. So this we are calling it as reduced instructions and complex instructions. Okay, so if it is a complex instructions, the number of instructions will be reduced. If it is a reduced instructions, that means simple instructions, number of instructions should be more. So the selection of instruction should be based upon the target machine. So we need to take care about that. Next, instruction ordering. Instruction ordering means here we need to reduce unnecessary load and store operations. So if you want to perform the same thing, a is equal to b plus c, so what we can do, so we can use a load operation, load, we can load b to register 1 and load c to register 2, and then we can add r1 comma r2. So the same thing can be written as, so load a comma r1, sorry, here we can write it a b comma r1, and load, or simply add c comma r1. So whatever the result we are having in r1, so for that c will be added, and now store the result r1. So here some sort of reduction is there here. So we have to remove the unnecessary load and store operations. We need to reduce the number of operations, the number of instructions. Okay, so that is the instruction ordering, which instruction should be implemented so that unnecessary instructions can be removed. Next, handling control flow. This is the most important in our source code, because the control structures means the if statements, if else statements, similarly while loop, for loop. So in all these cases we are using boolean expressions. So the result of these boolean expressions will be either true or false. So that means we need to give the addresses. So unconditional and conditional jumps we are using in this. So we need to give an appropriate and correct addresses to in the jump instructions. So if the condition becomes true, so the control should go towards which address. Okay, we need to give that appropriate and correct address. So that is the thing, handling the control flow, control structure. Okay, that is most important. And the next one, code optimization. So this is also very important, because every code should be written in a optimized results, which should give the optimized results. So here we need to reduce the number of memory or in terms of time also. So in this case, let us see an example. Let us take two instructions like t1 is equal to a plus 0 and t2 is equal to t1. So this can be reduced because we know that this instruction is completely not required, because if you add anything to 0, that will be the same value. The value doesn't change if you add with the 0, right? So we can remove this one and directly we can write t2 is equal to a. So you need not compute this step, and again you need not compute this step. So directly you can write t2 is equal to a. So in such case we can optimize the code. Okay, so this is also one design issue we need to concentrate while generating the code. Okay, next, handling data types. So we know that there will be a lot of data types. Okay, so the type conversion will be done. So sometimes the implicit conversion will be done and sometimes the explicit conversion will be done. So we need to take care about that thing also, right? So for example, let us take a is equal to some 5 and b is equal to some 2.5. So you know this is an integer value and this is a float value, and if you want to perform the addition on these two, c is equal to a plus b, so what is the data type of c? So if the data type of c is a float, obviously there will be a type conversion of a, type conversion on a. So there will be a type conversion because the type of the data type of a is integer, so e integer should be converted into float and then it will be added into the b. And if c is in an integer, c is declared in integer, then automatically some sort of data will be lost because the result will be in integer itself. So some data will be lost. So there will be a lot of issues here. So we need to take care about of all these data types, whether the data types are properly defined or not. Okay, next, calling conventions. Calling conventions. So calling conventions means mainly this is used in functions concept. So we'll be writing a lot of user defined functions in our programming. So while you write the user defined functions, what happened whenever the control executes the function call, the address of that particular thing will be moved into the stack. Okay, and then the control will move towards the function definition, and after completion of function definition, again the control will uh, resume its execution by getting the value from the stack, by pop the value from the stack. So whatever the what is the value available in the stack, that is an address, so that will be popped and the control will move towards that particular address. So the moving of calling function to called function and called function to calling function, as well as giving the input parameters from the calling function to called function, and so that is most important, and that should be taken care while designing the code generator. So the parameters, if there are any parameters, that should also be moved into the function definition. So how they can be moved, where they can be stored, everything comes here in the calling conventions. And the next one is error handling. Error handling. So this is the most important thing. So this is the output of any phase we have seen. So we have seen the lexical analyzer, semantic analysis, and syntax analysis, uh, intermediate code generator, target code generator, and code optimizer. So these are all different phases of a compiler which we have studied in our earlier sessions, and one input for everything is a symbol table, and one common output from all these stages is a error handler. So because in each and every phase, whenever there is an error, automatically that error should be reflected. So this error handling means identifying and reporting the errors. Reporting the errors. So if there are any error occurred, automatically that should be reported, and These errors we call them as a syntax errors. So we have studied in our programming language, the syntax errors are identified by the compiler, So the whenever the code was not written properly, so then immediately the syntax error will be raised. Okay, the error will be raised and that will be called as a syntax error. So all these are the issues need to be concentrated while generating the code, target code. Okay, so this is the last but one phase in the compiler design. So the input for this one is the intermediate representation, that can be either 3 address code, syntax tree, direct acyclic graph, or the postfix notation, anything. But we are representing a intermediate, 3 address code as a intermediate code. Okay, so I'll stop here, and if you are having any queries regarding all these issues, so feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.